Thanks for being here. My name is Fateme Baneshi, and currently I'm finalizing my PhD thesis under the supervision of Professor Manuel Soler and Maria Cerezo on the topic of network-level aircraft trajectory optimization to mitigate the climate impact using multi-agent reinforcement learning. Well, as the title of my thesis suggests, the main motivation of this study is to mitigate the climate impact of aviation. As my colleague already presented, like Alejandra and Raul Irane, aviation is one of the contributors to global warming through the emission of both CO2 and non-CO2 effects, such as, for example, countries. And due to the rapid growth of aviation, the aviation industry is facing pressure to reduce its climate footprint. Therefore, mitigation strategies are required to reduce the climate impact of aviation. For example, in terms of CO2 effect, several mitigation measures have been proposed, such as alternative fuel or technological advancement, for example, hydrogen-powered aircraft, as Raul presented, which they can also be beneficial to reduce non-CO2 effect. However, the main issue with these measures is that they are medium to long-term measures. We also need to have kind of medium or immediate solution. On the other hand, we have non-CO2 effect, which has been claimed to be their effect 2 times higher than CO2, though with high uncertainty, which can be mitigated using operational measures such as flight planning. This is because the aviation or the non-CO2 climate effect are highly depends on the time and location of the emission. Therefore, it is possible to identify areas of the aerospace which aircraft emission has high warming impact and try to avoid those areas. These operational measures are feasible with existing infrastructure, and they are kind of relatively immediate solution. So we can use them to reduce the climate impact of aviation. However, the main research question is that to what extent this strategy is feasible when it comes to practice. Here, for example, you can see 2 different sets of traffic. The left-hand side shows business as usual trajectories, and the right-hand side shows climate optimal trajectories. You can see that when we consider climate impact within the flight planning, we reroute traffic flow. For example, the climate hotspot areas shown in white would be evacuated. Instead, aircraft will fly on their neighboring sectors. So it can create congestion, which can adversely affect the overall performance of the air traffic management system. So to analyze or to see the true mitigation potential of flight planning, we need to analyze or study this problem at network scale to see the side effects. So far in the literature, many researchers have addressed this problem and explored the potential of mitigating climate impact through flight planning. However, as can be seen in the table, here we listed the most recent ones. All of them focus on micro-scale flight planning, which means that they only optimize individual trajectories without considering their network effect. For example, they have not considered the manageability of the traffic or the feasibility of this flight. Therefore, the climate benefit that they are reporting may not be truly achievable and may not be really reliable to be used as indicator to incentivize the stakeholders to accept or adapt these trajectories. Then the main research gap that we identified in this study is to analyze the potential of flight planning to reduce the climate impact at network scale. To address this gap, this thesis has set several objectives. The first objective is to quantify the operational impact of adopting optimized trajectory on the manageability of the air traffic in terms of potential conflict, like potential loss of separation between aircraft, because as we reroute flight, we may increase the probability of conflict, and also in terms of complexity, which is defined as the level of difficulty to manage a given traffic situation. Once we quantify this effect, we need to propose optimization strategy, so-called resolution strategy, to compensate for any negative effect. For example, if we are increasing the complexity of the traffic, if we are reducing the manageability, we need to compensate for that. And finally, to have kind of indicators to incentivize policymakers to adopt this trajectory, we need large-scale analysis. And for this large-scale analysis, we need a fast framework, a scalable framework, which enable yearly analysis of climate-optimal flight plan. So this would be the last objective of this thesis. The first 3 years of my PhD were devoted to exploring the first two objectives. And we proposed several sequential frameworks for climate-optimal flight planning at network scale. Within this framework, we first optimize individual trajectories. Then we assess their performance in terms of air traffic manageability using different indicators, addressing objective 1. And then we proposed several resolution strategies to compensate for the negative effect, addressing objective 2. The results and this framework have been presented in previous doctoral meetings, so I skipped them. But the good thing about this framework is that it provides the framework to analyze if it is possible to plan climate optimal trajectory at network scale, the feasibility of this measure, and they can be used for daily operation. But the negative point about this sequential framework is that they cannot be used for yearly analysis, because in the end, for each scenario, we need to optimize individual trajectory as the input. So the focus of this year of my PhD was to explore and introduce a framework to enable fast time evaluation of climate optimal flight planning for considering, for example, year scale analysis. The idea is to have a unified framework to give as input the business as usual trajectories, normal trajectories, and deliver manageable and climate optimized flight plan in one shot, meaning that addressing all the objectives at once. To this, and to mitigate the climate impact, we considered climate hotspot areas as constraint in the optimization problem and try to reroute them. And to address the manageability of the traffic, we consider air traffic complexity as the objective function, which needs to be minimized or at least maintained. This problem actually can be modeled within the framework of constraint multi-agent reinforcement learning. Formally, multi-agent reinforcement learning can be modeled as a constraint Markov decision process. How does it work? It involves the multiple agent interacting within the same environment. They receive observation state from the environment. Each agent takes an action according to the received observation, and the joint action of all the agents applied to the environment. As the result, the environment transit to the next step and provide a feedback of the reward and the cost penalty that each agent occurs. So the main goal of this framework is to find the optimal policy for each of these agents to maximize the expected cumulative reward while respecting some constraints. How do we use this framework to address the climate optimal flight planning problem? Here you can see the overall framework. We consider each aircraft in the aerospace as one agent, which are interacting in the same environment, which is the aerospace. They receive information about the traffic, for example, the trajectory data, information regarding hotspots area, and information on the neighboring aircraft. And then after receiving these information, each aircraft takes an action. It can, for example, modify its lateral route or vertical profile or speed. And the reward is defined as the reduction of the complexity, which we can reduce the complexity as much as we can. And the cost penalty is defined if or is occurred if an agent enter hotspot areas. So in the end, the aircraft will try to reduce the complexity while not avoiding climate hotspots. To see the performance of this algorithm, we perform an analysis on a real traffic scenario over European airspace for 2 hours. Here is the trajectories of the traffic that we considered, and we applied the proposed framework. We showed here the results, and we compared the two different routing options, business as usual trajectories and trajectories obtained from our proposed approach. First, we see the control climate impact. We can see that by applying the proposed strategy, we reduce the control climate impact by 79%. Also, we reduce the air traffic complexity by 17%. And finally, all these benefits come at a slight increase in the operational cost, which increased by 0.8%. To have better visual understanding of these results, here we showed the climate map and the complexity map of original trajectories and generated trajectories using our approach. Here you can see that, for example, for business as usual trajectory, we have some warming impact, and we are trying with our algorithm to reduce this warming impact while maintaining the complexity of traffic in this level or reducing it. And here are the results generated from the trajectories from this algorithm. You can see that to large extent, we could successfully reduce this warming impact, and also we could reduce the complexity in some areas. So it shows the promise of this algorithm to be used for analyzing or evaluating the potential of climate optimal flight planning in practice. Some outcomes of my thesis so far reported or documented in papers. Some of them are in preparation. We have presented this result in several conferences, and I did my research stay last year at EPFL University, which I've been focusing on developing this multi-agent constraint reinforcement learning to address this problem. As the very final step of my PhD thesis, I need to finalize my thesis and just writing. Thank you so much for your attention.